Hi, my name is Philip. Today I will talk to you about cross-level high-utility item set mining. It is a topic in data mining, a task that we can do to analyze the data. We'll learn together what it is, how it works, and I will show you many examples also. Okay, so let's start. So I think if you know about data mining, you probably know about frequent item set mining. Frequent item set mining is a popular task we can do to analyze the database. So the classic example for frequent item set mining, to explain it, is about shopping. So here I will give you a brief example, and then I will explain some limitation and then talk to you about the cross-level high-utility item set mining. So frequent item set mining, what it is. Let's say we take the example of shopping to make this simple, okay? So here as input, I have what we call a transaction database. That means a database of transactions, what the people buy in a store. So here in this database, we have 7 transactions, T1 to T7. The first transaction is AC, like apple and cake. Transaction 2 means someone bought the E, the eggs, for example, the item E. Transaction 3 is items A, B, C, D, E. That means like apple, bread, cake, dates, and eggs, for example. So we have a database like this about shopping. And then, as the user, we must choose a parameter called the minimum support, min-sup, okay? So that means we want to find what appear many times in the data. If we set min-sup to 3, that means we want to find all the frequent item set, the sets of items or products that the people buy at least 3 times, okay? So in this task, if I set minimum support to 3, this will be the result, what I want to find, the frequent item set. So let's have a look at this together. For example, if you look at the frequent item set AC, it has a support of 4. Why? Because AC has been bought 4 times in the database. AC, 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 and AC. Okay, 4 times. So 4 is at least 3 or more. So AC, buying AC together, is a frequent item set. So all the others also here are frequent item set. So this is a very classical data mining problem, finding the frequent item set in a database. Not just for shopping, it can be applied to many other fields. For example, it could be web pages, A, B, C, D, could be web pages, and we want to find the web pages that the people look, okay? The same people will look at the same web page maybe, and so on, okay? So to do frequent item set mining, there are many algorithms like a priori, ECLAT, FP growth, and others, okay? But all of this is useful, but in the real life, if you think about shopping, finding the items that the people buy many times is not necessarily the most interesting for the business. What is interesting for many businesses is the money, actually, okay? So there was an extension of frequent item set mining called the high utility item set mining. It is a more general problem. In this problem, the goal is to find the sets of items, the item sets, that yield a lot of money, okay? That maybe are not frequent, but make a lot of money. So the input is like this. Again, we have a transaction database, like about shopping. So this one has 7 transactions, but here there is something different because the items have some numbers, some quantities here. So what does it mean? So in transaction 1, we have A1. It means, for example, 1 apple. C1, 1 cake, okay? So here we have quantities. It tells how many apples or how many cakes you have. So for example, if you look at T5, T6, okay, we have A2, 2 apples, 6 cakes, 2 eggs, and so on. So this is some additional information. And then also we have another table called external utility, means the unit profit of the item. If you sell 1 apple, how much profit you earn, okay? So 1 apple is a $5, 1 bread, $2 profit, 1 cake, $1 profit, and so on. And then in this problem, we need to set a parameter called the minimum utility, the minimum amount of money, okay, min util. So the goal will be to find all the high utility item set, the item set that have the money or the utility at least $30 in my example. So this will be the result what we want to find in this database, okay. For example, we find that BCD makes $40 in this database. It is at least 30, okay? So we say it is high utility item set, and this is in the result. Now, I did not explain how to calculate the money. Let me explain this to you in more details, okay? Because I think you want to know how do we calculate the money. So, how to calculate the utility or the money in this example? Let's say we take an example, okay? We want to find the utility of BCDE. That means BCDE, that means you buy BCDE together. This is important. Not just BC, not just DE, okay? The utility of BCDE means the money when the people buy BCDE together, must be together. So to calculate the utility of BCDE, you need to find BCDE. It appears in T3, okay, we have BCDE. So we have 5 bread. 1 bread is a $2, so 5 multiplied by 2. 1 cake, cake is $1, so 1 multiplied by 1. 3 bags of dates for $2, 3 multiplied by 2. And then 1 egg for $3, so 1 multiplied by 3. So this is for T3, okay, we have BCDE. Now, BCDE also appear in T4, right? So we do the same thing. In T4, we have 4 bread for $2, okay, 3 cakes for $1, and so on. So the result of all of this will be $40 if you do the sum, okay? So this is how we find the utility of the item set, how we calculate the money. So this problem, high utility item set mining, is interesting because it has some practical application, like find what makes the most money in a store, okay? It could be applied to other things. But also, it is a difficult problem. Why? For 2 reasons, okay? First, the search space is very large. If you want to find the solution to the problem of high utility item set mining, you need to look at many combinations of items, like A, B, C, AB, AC, AD, BA, BC, and so on, okay? Then ABC, BCD, and so on, and then ABCDE. So there are so many combinations you can check. So we don't want, if we want to make an efficient algorithm, we don't want to look at all the possibilities. And another problem is the utility is not anti-monotonic or monotonic. So let me explain to you what does it mean, okay? That means that if you have an item set, the utility of this item set may be equal more or less than the utility of its supersets. So for example, let's have a look. BD may yield $30 of utility or profit, but the superset of BD, like BCDE, can make more money, like $40. But the superset of BCDE, like ABCDE, can make less, only $25, okay? So what does it mean? if you have BD, the superset of BD maybe can have more money or less money. We don't know, okay? So because of this, it becomes difficult to eliminate some possibilities when we search for the high utility item sets. So why is it like that? If you have BD $30, you have BCD make more money. Okay, why? Because maybe you buy more things together, so the money should increase. But when we have ABCD, it should be DE, the money is less. So why? The reason is, even though we buy more things, okay, it will appear less often, okay, not so many times, so the money will decrease. That's the reason. So this is a classical problem. To solve the problem of high utility item set mining, there are many algorithms. Some of the fastest is HUI-Miner and FHM, for example. There are others. So the key idea, without going into the details, these algorithms will use some upper bound on the utility, like the TWU, that are anti-monotonic, to be able to eliminate some possibility and still find the correct result. So I will not go into the details about this, okay? I made some other video to explain the FHM algorithm, for example. If you want to know how it works, you could look at this in more details. Now, I want to talk to you about some limitation of high utility item set mining. Okay, this is the topic of today, okay? So, high utility item set mining is useful to find the item sets that are profitable, make a lot of money in a database. But one limitation that is important, it does not consider how the items are organized in taxonomies. That means in the real life, the items, for example, in the store, they are into some categories or taxonomy. For example, if you look on top, here we have a taxonomy, like a tree, okay? Different categories of food. So we have food, we have wheaten food or steak, and the wheaten food made of wheat is like the bread or the pasta, okay? And we have other category like the beverage. We have the Coke, the cola, or the water, okay? So in the real life, in the store, we have the taxonomy. For example, we have the milk. Maybe we have different types of milk and so on. So considering this information is important, okay? It tells us something. So to be able to find the item set using a taxonomy like this, there have been some papers about this in the past, like the multi-level frequent item set mining. So that means you can find the frequent item sets using the taxonomy like this. For example, you could find many people buy food with beverage. But beverage can be any beverage. It could be Coke or water and so on, okay? So in these problems, we can find the item set that are frequent, and the items can be from different levels in the taxonomy. We could have food with beverage or Coke with water and so on. So in high utility item set mining, there was one algorithm for the multi-level high utility item set mining called ML-HUI-Miner. It is based on HUI-Miner, and what it will do, it can find the high utility item set, make a lot of money using this taxonomy, for example. So, but one problem about ML-HUI-Miner is that the limitation of ML-HUI-Miner is that it cannot find the cross-level patterns. So let me explain what does it mean. Okay, so that means that ML-HUI-Miner can find high utility item sets using items, any items from the taxonomy, like food with beverage or wheaten food with steak and so on. But one limitation, it cannot find the cross-level patterns. What does it mean? It means that ML-HUI-Miner always find the item set where the items are from the same level in the taxonomy. For example, it can find bread and pasta together because they are the leaf of the taxonomy. Or it can find food and beverage together because they are the second level of the taxonomy. But ML-HUI-Miner cannot find the item set beverage and pasta because beverage and pasta are not at the same level in the tree, in this taxonomy. Beverage is second level and pasta will be the fourth level if you count from top to bottom. Okay. So to solve this problem, I and other people, we have introduced a new problem called the cross-level high-utility item set mining. The goal is to find some high-utility item sets that can contain any items from the taxonomy and yield a high profit. And there's no restrictions on the different levels. Okay, you can mix any of these items. So in ML-HUI-Miner, you cannot do this. The items must always be from the same level. So this is not so good. Okay. So in the new problem, cross-level high-utility item set mining, we can find the patterns like bread, steak, and beverage. Bread, steak, and beverage. All these items are from different taxonomy level in this tree, okay? And this maybe make a lot of money. And if you use the high-utility item set mining or multi-level high-utility item set mining, you cannot find this pattern. So this new problem was proposed in this paper. So let me show how it works. Okay. So how to calculate the utility if we have a taxonomy like this. So I will explain with some example to make it easy to understand. If you want more details later, you can have a look at the paper also or try the code and see how it works. Okay. So first, for the utility, we can have the utility of the items like BCD. These are the normal items we find in the database, the leaves of the tree. Okay. So in this case, there's no difference with high utility item set mining. We take the like B5 for BCD. Okay, we find BCD. We have 5 bread for $2. We multiply like we did before. 1 cake for $1, 3 dates for $2, and so on. So this is the same as before, no change. Now there is a second case that will be different. It is when you have the what we call the generalized item set. Generalized item set means you have some items that are not the leaves in the taxonomy. Okay. So here, for example, we have Y and C. So Y is not a leaf in the tree. It is a category, or what we call a generalized item. So how to calculate this, the utility of Y and C? We must explain. Okay. So to do this, we must find all the transactions that have Y and C together. So Y could be A or could be B. Okay, so that means Y and C is the utility of AC or BC actually. Okay, So here we have A and C. A is okay, it's like Y, okay. So 1 apple for $5, 1 cake for $1. So 1 apple for $5, 1 cake for $1. This for transaction 1. Then again, in transaction 3, we have A and C, but we have also B and C. Both of them, A and B, can be Y. So we'll have 1 apple for $5 plus 5 bread for $2 plus 1 cake for $1. Okay, this is for transaction 3. Then we do the same for T4. We have B and C, T5 A and C, T6 AC, and T7 BC. And this will tell us the utility of this generalized item set is $61. Okay. So this is how to calculate when we have the categories or what we call the generalized items. Now let me give you the problem of cross-level high-utility item set mining. What is the definition? So we have the same type of database as input, and we have the minimum utility threshold. But now we also have a taxonomy like this, okay, with some categories. As you can see, in the transaction database, we cannot see the categories. There's no X, Y, and Z here, okay? But we have the items, the leaves, in these transactions. And then the output is to find out the cross-level high-utility item set. That means the generalized item set that have the utility at least equal or greater than the minimum, like $60 in my example. So this will be the result we can find. Okay. So if we use high utility item set mining, we will miss a lot of these results actually. Okay. But now we can find the item set with the categories like E, Y, and C. Okay. If you buy E and C with Y, which can be A or B, this will be the result. Okay. So this is very interesting, I think, for the practical application. So how can we solve the problem? I will not explain all the details today because I just want to make some introduction. Okay. And you could also read the paper to see more details. But I want to give you the main idea about how to solve the problem. So the first algorithm for cross-level high-utility item set is called CLH-Miner. It is based on HUI-Miner, and it will explore the search space by doing two types of extension, what we call the tax-based extension and the join-based extension. So let me explain a little bit how it works. Okay. So this is the search space. If I have this taxonomy here, the search space will be like this. That means all the combination I can make, okay, for the item sets. So first we have the empty set, the people buy nothing. Then we have the people buy something from category X. Then we have the category Y, which is a special case of X in the tree. And Y could be A or could be B. And also we can combine B with A to make BA. Okay. From the category X, we could make C. C is a special case of X. And from C, we could add another item, another category like Y. Then from CY, we could change Y to CA or to CB. And then we could combine CA and CB to make CBA and so on. Okay. So I will not do the proof, but we can represent all the combinations using a tree like this. And to explore this space, this search space, we only need to do two operations. we call the tax-based extension and the join-based extension. Let me explain what it means. Okay. So here I use a smaller search space to explain the idea. Okay. So what is a join-based extension? Join-based extension means you take two brothers in the tree, two siblings in the tree. Okay, here I have X and Z. I combine them together to make ZX. Okay. So this is a join-based extension. I take two siblings in the tree, like X and Z, to make ZX. So we say ZX is a join-based extension of Z. The second type of operation I need is the tax-based extension. So let's say you have an item set like CY. Okay, Y is a category. So tax-based extension means you use the taxonomy to replace the last item like Y. It is a category. You replace Y by some item that belongs to Y, like A or B. Okay, so CY transform into CA or CB. So this is what we call a tax-based extension. You have a category and you replace the category by a more specialized item like A or B for Y. So the algorithm will use these two types of extension to search for the cross-level high-utility item sets. Also, in the paper, if you read the paper about CLH-Miner, you will see they use a special data structure for each item set called the tax utility list. Okay, so here I will not explain all the details because it will take too much time. Okay, but it is based on HUI-Miner. If you know about HUI-Miner, you know that algorithm use the utility list to find the high utility item sets. Here we use the tax utility list. So it is a modified utility list where we have some more information about the taxonomy, about the tree. So for an item set like Z and Y, we will keep some information about the child of Z, like they are of Y, sorry, okay. They are A and B in the tree. So that will be the main difference compared to HUI-Miner. So if you don't know what I mean, it's not a big problem, okay. This is just some details. So I will skip some details about this, okay. If you want to know how the algorithm works, you can check the paper for more details. Now, one key aspect, if we want to design the quick algorithm, is we need to be able to reduce the search, eliminate some possibilities. So to reduce the search using the taxonomy, we use two measures called the GWU and the REU. So I will not do the proof here, but this will allow to calculate some upper bounds to eliminate a lot of possibilities in the search. So it will tell you, for example, the supersets of AB cannot be the cross-level high-utility item set. So we don't need to look at them. Okay, so I will skip the details about this. So this is the code of the algorithm in the paper. Okay, if you are interested, you could check the paper or download the code also. So in that paper, we did some experiment to evaluate the algorithm. To evaluate this type of algorithm, we use the shopping data. We have two databases. This is the public data. These are the public database. Liquor is data, shopping data from a store that sells the alcohol. And Fruit Hut is a fruit store, okay, that sells the fruit. So here we have the number of transactions, the number of items, and the number of categories, the generalized items. And we have the number of levels in the taxonomy and so on. So in that paper, some experiments were done, okay, to evaluate CLH-Miner. So here I just show you briefly to see how it works, okay. So for these two databases, there was some experiment to show how is the speed, the time, okay, to find the solution, depending how we set the minimum utility. And here there are three versions of CLH-Miner with different optimization. And this shows that the optimized version on top is the best, okay, in this experiment. So this is the kind of experiment we do to evaluate this kind of algorithm. Now, something more interesting we can find in this paper is that we also have the data about the number of patterns here. Okay, so here on the two databases, liquor and fruit hot, we compare the number of patterns we find. Okay, so for minimum utility equal to 10,000 on liquor, we have about 5,000 cross-level high-utility item set. If you find the multi-level high-utility item set, you only have 200. And if you find the high-utility item set, you find 241, okay, more or less. So what is interesting here is that using the cross-level high-utility item set, you can find a lot more item sets, actually, because you can combine the categories, so it will find more item sets here. So this is the main idea. There are more details. We can compare the time also, the memory, and so on. One thing important to see is that for the time, CLH-Miner take more time than HUI-Miner or ML-HUI-Miner, because when we use the taxonomy, we need to look at more possibilities than if we don't use the taxonomy. So it will take more times, we will find more item sets. So this is the main idea, what we can observe here in these results. So CLH-Miner is the first algorithm for cross-level high-utility item set mining with a taxonomy. But there is one limitation. Sometimes it can be difficult to select an appropriate minimum utility value to find the desired number of patterns in the data. What do I mean by this? If you are the user, you need to set the minimum utility, okay? But if you set too low, you will find maybe millions of patterns, and the algorithm will take a very long time. And if you set too high the minimum utility, you will not find enough patterns. Maybe you don't find any. Then you need to run again and so on. So one question that appears from this is, could we design an algorithm where we don't need to set the minimum utility? Okay. So the solution to this is a new algorithm called TKC, designed in this paper. So the idea is we can change the cross-level high-utility item set mining problem to the problem of top K cross-level high-utility item sets. So here a new algorithm called TKC is designed to find the top K cross-level high-utility item set that make the most money, and we don't need to use the minimum utility. So let me show you how it works. Here I have the example, okay, just to give you the main idea. I have the same database I had before, okay, but here instead of setting the minimum utility, I need to choose a value for k. So for example, if I set k equal 5, it means I want to find the top 5 item set, a cross-level item set, that make the most money. Okay, so this will be the result. So it can be said that this is more intuitive than CLH-Miner, because how to set the minimum utility is not so easy. But here you can say directly, I want to find the top 5 or the top 100 item set that make the most money, okay, using the taxonomy. So this is interesting. So there is one algorithm called TKC to solve this problem. So when we use TKC on the real data for shopping from the fruit store, for example, if we say k equal 1000, we can find the patterns like this. Like people like to buy the beans with the cherries, and this make a lot of money. And beans in the taxonomy is a generalized item, means a category, because there are different types of beans. So if you use the high utility item set mining, you cannot find this pattern. But with TKC, you can find the patterns like this that make a lot of money. Another example, in the other database about alcohol, we find the patterns like this. Okay, also, these are categories of alcohol that people like to buy together. So, I have introduced the problem of cross-level high-utility item set mining. I would like to point out some key papers about this, okay, I talked about today. So, Cagliero is the person introduced the problem of multi-level high-utility item set mining and the ML-HUI-Miner algorithm. Okay. Then, in another paper, I introduced the problem, the more general problem of cross-level high-utility item set mining and the CLH-Miner algorithm. Then, in another paper, this problem was changed to top K cross-level high-utility item set mining, and the TKC algorithm was proposed. Then after this, there has been some other algorithms, but I would say these are the key paper that defines the problems actually, okay, not just the performance improvements. So in conclusion, today I have presented the problem of cross-level high-utility item set. I have talked about one algorithm called CLH-Miner, and I have talked about top K cross-level high-utility item set and the TKC algorithm. If you want to try this, like the CLH-Miner algorithm, you can find the code in the data in the SPMF library. It is free to use, open source. If you want to do research, improve the algorithm, you can find the code. And also there are some other algorithms also available, okay, related to this. So you can try and have a look how it works, okay. So that's all for today. I hope it has been interesting. You can also check out my other videos if you want to learn more about the pattern mining. Okay, thank you. See you.